Hello, very good afternoon. Welcome to this talk on robots in the wild. We're going to look at many different robots today. My name is Marc Hanheide. I'm a professor of intelligent robotics and interactive systems at the University of Lincoln. And very pleased to have you all here. And we're going to dive right in a second. This is all part of our lecture series, Christmas lecture series at the University of Lincoln. And I'm really pleased to continue our theme on robotics. So we had Paul Baxter already on Monday talking about social robots, and there's some links here that also fit with that. So when I'm talking about robots in the wild here today, I'm not really talking about this, right? We're not talking about robots going out into the forests or in the jungle or anything like that. I'm also today not primarily talking about this. So some of you may have seen this sort of industry robots doing very repetitive tasks in manufacturing. A lot of cars these days are fully automatically constructed through robots. And you've seen this massive uptake of industrial robots over the last couple of years. But that's also not so much what I'm talking about this. So it's not this either. What I'm talking about, or what I mean when I say robots in the wild, I'm talking more about things like this. Robots going out into pedestrianized areas. So this is a video in the center from a robot that has been running in Munich in Germany. And on the right-hand side is a robot there that I'll also talk a bit more about. That's Werner in a care home in Austria. And on the left, I've just put a little photo of trying to teach kids about robot programming in a primary school here at Lincoln. So it's when these robots kind of leave their cages, right? They're normally behind bars. They're working, these industrial robots work behind bars, doing very repetitive things, building cars, etc. What I want to really see is robots leaving these cages and go out into the, wilderness. You could even say the hostility of human habitats. So when they are surrounded by people, when they have to somehow do their job among us. I think that's something that has been, for myself, been a very interesting journey over the years to build autonomous robotic systems that can go out and work with humans, alongside humans. One of the kind of key words of that one is also cobots, so it's collaborating robots in that sense. And whenever we talk about robots working with humans or in the vicinity of humans, one word that needs to come up and needs to be considered quite often is trust. So some of these slides actually come from a seminar that we had last year, which was called Trust in Robots. There was a whole series that a lot of researchers came together and see how can we make humans trust robots, or what are the aspects of trust. And I'm not going to refer to many scientific publications, but the first one I'm going to refer you all to here is not a robotics, it's not a computer science paper, it's actually a philosophy paper by a quite well-known philosopher, Bertrand Mallet. And he looked at the kind of multidimensionality of trust. And I like this sort of categorization of different trusts you could have here. And this is, on the one hand, we've got so-called capacity trust. That is, you trust a system, whatever it may be, an electronic system, maybe even your phone, to actually do the job it's supposed to do well, right? So we all just believe, yes, it's about reliability, it's about predictability, and that it has the capacity to actually achieve a task. The other aspect is moral trust. That's not so much how it actually does it, but what it does. Right? Is that something that we would consider ethical, respectable, etc.? So what I'm going to focus on most in my talk now is on capacity trust. So that is really about how we make sure that these robots do their tasks well. So I'm not going to touch so much into the morality aspects here. We've seen some of those aspects also in the talk by Paul Baxter on Monday. So if you want to look back at that in our lecture series, there's some aspects also on regard to that and how we actually interact with humans. Here I'm mostly concerned at the moment, just making sure that they actually have the right capacity and that people can show trust to these robots because they trust that they can do their job right. Now, looking at this, here's a kind of overall figure that I think is very important for this capacity trust. What we have seen in lots of robot systems, and we've shown the industry one before, there may be some trust there that they really do their job well. And we know this, if they just repeat the very same thing all over again, you can probably have quite some trust in their capacity to actually build a car. Now, once they actually go into human inhabited spaces, they need to be much more flexible. And we must see that they actually improve and adapt to their environment, to their scenario, and to us humans. So we want competent robots, we want robots that are reliable, but we also want them to be able to adapt to ourselves. And this cycle that I've shown here is something that come from a project that we've done at the University of Lincoln with a number of European partners that was called Strands, where our focus was really that we have robots that begin having some autonomous behavior, but it doesn't stop there, right? It doesn't just do the same thing again and again, but we have them deployed for a long period of time. They go out into everyday environments and they use that, what we call deployment, that they are out there. We use that to learn from the exposure that they've got there. And that means that hopefully their performance then improves. And then we have better behavior, we can achieve longer run times and higher acceptance and so on. So we kind of close this cycle. That kind of takes in input from a lot of different disciplines that we in computer science are very excited about, namely machine learning, artificial intelligence, and human-robot interaction. So really the kind of what have always kept me going was to keep this cycle spinning. And in that sense, when we say we need to improve, it also means to keep capacity trust. We must see that the robots are not stupid and are not doing the same stupid mistake again and again. And, we can't be around as programmers all the time when we see, oh yeah, it's done something wrong, let's fix it. We can't do that if we have these robots going out into the wild, basically beyond our control, and have to survive on their own to some extent. So, I said this is my personal robot journey, if you want, right? I started off at the University of Bielefeld in Germany, then worked at the University of Birmingham, and then came to Lincoln in 2012. And so we've explored this general theme for quite a long while along this journey. And as you see towards the end now, we've got quite a number of different robots that we look at and trying to actually embed this sort of adaptation and full long-term autonomy into a couple of different robots. So let's focus on just some. We don't have the time, and I'm not going to bore you with my life story of what I've done in robotics. But I'm going to start with a project that I've already mentioned before, and that was the Strands project. That was a European project, excited to work with a lot of different partners all over Europe, in Austria, in the UK, in Germany, and in Sweden. The focus here was really long-term autonomy in everyday environments. And it was also interesting. So we learned a lot on the way, right? So we said, like, all right, we came from a very algorithmic perspective. We just want to put these robots out there and we want to kind of apply some machine learning so they get better over time. So we kind of ignored to some extent this sort of human-robot interaction, social dimension, and the trust aspects. And that's something where we've learned a lot as we go along, and I'll show you some of these lessons we've learned, and some of them are mildly entertaining, I should say. You've seen this one before, so that's the sort of thing that kind of kept the whole process going and is still kind of an underpinning paradigm of a lot of the research work I do at Lincoln these days. Now, this Strands project, and it had different sort of aspects. We had robots going into security environments and also some sort of environmental monitoring aspects. But one interesting aspect was that we had a robot that was in a care home. And because it's a European project, it was not actually a care home in Lincoln. It was one that was down in Vienna. So about 1,000 miles away. And that also meant we couldn't be there all the time, right? We had to run it from here. And that meant running it from here as well. We could do a little bit of monitoring. You see some of these sort of interfaces we had used to actually monitor how it goes. And the robot would shout at us if some things would go wrong. And, quite often things go wrong. So this robot was out there for about a year, actually mingling among residents of a care home. And that for us was a very exciting challenge, and it had different tasks to do there. And I'm only going to talk really about one of them. So one of these tasks that this robot had to do there, completely on its own, had to navigate with people that were in wheelchairs, with people that were walking around, and that had very, very little experience to that point with technology. So this is our robot Werner. As I said, it was developed in cooperation with people in Austria. So we have a very similar robot here. We've got actually two of them at the University of Lincoln. Same sort of robot, different color. The info terminal in this setup was, you could just say it's an iPad on wheels, a touch screen that had several functionalities where people could get information about the food that was on offer in the cafeteria, entertainment, photos, general news, weather forecasts, etc. So in a way, you could say the same functionality could just be provided by a handheld, iPad or something like that. Now, where it gets interesting is to actually use the embodiment so that a robot actually is physically available, and that it can autonomously drive around. So it can actually attract attention, and you can actually provide services to people where they are in their environment. They may not even immediately feel the urge to do that, because they could have just taken the phone or something like that to access the similar information. But this is a robot that kind of makes itself available, and people could use the opportunity to actually interact. So one question here was, if we go out into this environment, there's a lot of different challenges, as I said, just from the navigation in these human inhabited places that I'm not going to go too much into detail about. But one question that we had there was, how can we get better in delivering these services? So how can we actually make sure that we are at the right space, at the right place, at the right time to provide this robot? So it's no point of just going around when you don't meet people, right? This robot was autonomous. It could go around anytime. It could go anywhere in this care home. But what's the point if it's not being used? And that's exactly something that comes with capacity trust. If you think about that this robot is there to provide information, you would think it's bloody stupid if it just happens to always be somewhere where you don't need it. And you can only learn these things on the job, right? You don't know exactly how people are going to use it, so you want to actually adapt how they're doing this. And that's a question for machine learning. And this is a whole field in machine learning, and we teach this subject also at the University of Lincoln in both our MSc and BSc programs. So it's just one of the many things that robots can learn, or autonomous systems can learn on their own. And here the challenge is, obviously, we can't pre-program it. We want to see that it gets better on the way. And we started off from a kind of, from an observation about human life. Obviously, we also know that our lives are very, dynamic. It's not static. We don't have the very same thing every day in the gate. So the robot will actually cannot just assume that the world is static. People may change their behavior, or at least they will have certain ways, certain desires that will change over the course of a day or over the course of the week. So that's an observation that we had there. That actually our life is not static and our world is not static, but that indeed it is full of routines. Right? Especially in a kind of setting like a care home, there are a lot of these sort of routines. Some are daily. You've got you wake up in the morning, go to bed. You've got your meals that are kind of scattered around the day. You have weekly routines. So some people may have certain events happening only at certain days of the week. Then there's obviously the weekend and the weekdays where things will change. And it's kind of a general observation that while we always say our life is not very predictable and we have all sorts of things to adapt to, at the same time, we've got a few routines that we go through all the time. And the idea was, can we capture those routines? Can we learn these routines and by this get better over time in delivering our services? So I'm going to talk a little bit about the underlying machine learning bits here. And this is the sort of typical thing that we would try to do in machine learning, is that we have some sort of states that we observe. So here an example is, where is the robot when? Right? So it's just a location and a time. And if it was there at that location and at that time, did people use it? So we are trying to map from predict, basically from being at a specific location and a specific time, onto what's the chance of success. And success here just means, did people use this robot? It's very much boiled down, simple thing that we're trying to do, which you find all across machine learning, is you have something that you can observe, you have something to predict, and you're trying to learn this mapping from one thing onto the other. And that could be all sorts of different things. Could be, if you see this, you do this. If you see this, that means. If you have, that could be many, many different things that are all around machine learning. It's always this sort of formulation of saying, well, we've got something, and here, so we have some observation, and we are running some sort of machine learning, and it gives us a prediction of what it could be, or what sort of comes out of that. And some method that we have developed here at Lincoln is this so-called spatio-temporal modeling. And that is really a machine learning method that you could use for many, many different aspects. The main point is you're really trying to find these periodicities. And there could be several of them, what we call superimposed. So you've got one that fluctuates very fast, another one slower, and you could put them on top of each other if you want. And you get a more complicated model that is not just one period. And that was called frequency map enhancement, or Fremen for short. And it's a machine learning technique that allows us to learn from relatively sparse data, from just a few examples already, to make predictions basically any time into the future. So we could then, if we have learned this model, it allows us to say, right, this location at this time, what's the chance of actually getting somebody to interact with me? That was the main idea. Now I'm going to even put some formulas on, just to blind you in that sense. We don't have to think too much about this. The key aspect is, for all these self-learning systems, is always the problem of exploration versus exploitation. And we need to balance them off. What does that mean? Exploration means that the robot is trying to find new data, finding new situations, basically looking for opportunities to learn. And exploitation means just doing what is currently the best. So in that sense, we have this general principle, exploration versus exploitation. And if we just do exploitation, we will never learn anything. If we just do exploration, we would just randomly walk around and look relatively stupid. So you want to balance these two off. You want to have a little bit of exploration so that you have a chance to learn something new. And you want to also have some exploitation so that you're not just doing stupid. You want to search around basically the things that you already know work quite well. That's kind of common principle, again, for having systems that need to learn on the job. They need to, if they only just do based on what is they think is best at the moment, they will never learn anything new. And if they just explore all the time, they will basically be stupid and not improve their behavior. And a simple way, we've done, you can do a lot of research in this. What is the right ratio between exploration and exploitation? How far do you want to plan ahead? I'm not going to talk much about that now. Right? The general principle is finding the best trade-off between this exploration and this exploitation when you've got these systems. And here's a map. So the robot did these services in a couple of places around this environment here. And we see that the success in this was quite varied. So we see that we had very successful interactions here in these colors. So the orange one is the one that had the highest success in effect over this period of time. And that was probably because people tend to wait at lifts and probably thought like, oh yeah, all right, I'll wait here anyway. I can use this robot. Very low success when the robot went there was at this info board. And indeed, this part here is the sort of administrative wing of the care home. And as such, there were not many customers, not many residents there, and it wasn't very much used. The size of these stars indicates how intensive the use was. You'd probably be not surprised to see at the kindergarten, at the nursery, that's also embedded in that particular facility, received most of the clicks. So kids tend to kind of just be very curious and keep going. And the main message for us here, and this is a simple graph, but it shows an upward trend. And this upward trend is what was really exciting for us, because what you normally see when robots go out into the wild is there is a sort of novelty effect. People are very curious and play with it at the beginning, but then they lose interest because, oh, I've seen all this. And we managed in this system to kind of beat that trend. We had an upward trajectory of how successful it was, how often people used it. And that just kind of shows the principle that you can get better on the job. Right? So people actually, because the robot was available where they needed it more or where they wanted to use it more, it actually got higher value. Its capacity increased in that sense. So that was a very good story. I'm not going to talk a little bit about things that can diminish trust and that can destroy trust very quickly. And these are mistakes. If things go wrong, one experience where things go wrong and people lose trust in the capacity of a robot very, very quickly. Things can go wrong in many different ways. And some are quite fatal, some are really bad, and some are just like, oh yeah, it's not very clever, is it? So what we see here, this little graph here is basically we allowed the therapists in the care home to use that robot if they wanted. It was programmed to support them in some therapy sessions. And we see that the robot was used in like 1/3 of the time. They were completely free to decide to do it. Most of the cases where it wasn't used was because they had actually cancelled the therapy session. But sometimes there were technical problems, and sometimes they decided, no, we don't want this today. And most of these cases when they didn't want to use it, that was following on from technical problems. So, something didn't work, and that meant people said like, oh, right, I had enough of this. It's just a burden. I'm not going to use this robot anymore. So there's actually a temporal thing that you don't see in this little pie chart here. And what can go wrong? Well, things can go wrong really badly. That was one of our robots had fallen down the stairs. Massive, massive issue on the trust that just even the managers in that care home had on this particular robot. And what was the problem? It wasn't an algorithmic problem. It was, as ever so often, human failure. Somebody had disabled one of the safety features of this robot that would stop it from going down the stairs. And this is a functionality that you may even know if you have a robotic vacuum cleaner, a Roomba. It can detect stairs. And it's a similar system that was in here, but it wasn't running. So we actually must make sure that our software is robust and that indeed it lives up to the specifications in many ways. And I can tell you that this experience of having seen this robot, or heard it even just falling down the stairs, has destroyed trust completely. It took us many, many weeks even to kind of, build it back up and allow this to run again. So that's one overall problem. If something fails, it diminishes trust very, very quickly. And here's another kind of graph that shows this, where we see kind of what was the rating. So this is a subjective rating by the therapists using a robot in these sort of sessions. And here is the moment when something went wrong. And you see this is a kind of a timeline when they used it over this deployment. And we have never recovered in this particular session, this kind of Thursday therapy session. There was one problem where it just didn't perform as it should have. And even if it worked perfectly well after that, next time it worked absolutely fine. It just had destroyed it forever. So this is a kind of graph where there wasn't any technical problem and actually the rating went up. If you have a big problem, it just goes down. So we need to have actual reliable and stable systems. So this is then where robotics is not just purely about robotics anymore. It touches onto software engineering, continuous testing, etc. So we have actually going into different aspects of computer science to build these systems. How can we gain capacity trust back? So if things are not working or a robot is not very good and makes mistakes, and that's quite normal, it always will happen. Right? If we go out into the wild, these robots will not perform to their optimum and they will make stupid things. One aspect that we've actually discovered, it's actually good to involve humans, provide them with some agency, get them to actually help out a robot. Right? So here's one. This robot. This is in an office environment in Milton Keynes. Similar type of robot. It can't open doors. You may have seen it. It hasn't got hands, so it actually relies on humans to help it. So it engages in dialogue with them, right? And then asks them to hold open the door, and eventually will go through. People accept that much more than a robot just standing there and beeping because it can't reach its destination. So actually, dialogue and engagement with humans can help to build trust and to maintain it or even to repair it. Now, I've also mentioned before, one mustn't make the same mistake all over again. And what we see here on the kind of right-hand side on this map here is all the little different places where over this long period of time, a robot had failed to navigate properly. It would eventually recover, but that was, it just couldn't really reach the place properly because something was in the way, or it just got lost a bit. And that's not acceptable, because eventually it will, it needs to carry on with this task. And what is a way to recover? Well, we've seen we can ask humans to help us, but they may help once or twice. But if they don't see why the robot needs help and it has to be supported and helped again and again, well, then you will really see a decrease of this trust again. So we should really learn from this, right? If somebody is willing to help a robot, then we should use that knowledge, and we should use that additional information to get better and not do the same stupid thing again. And that's another kind of aspect of, you could say, machine learning that we've used here. We've had this robot going around for a very long time, 362 kilometers over this sort of time in this particular system here. And there was a lot of problems here. And sometimes when it can't actually go from one place to another, it will ask for help. And very rarely you will get some help, because there's somebody around who is willing to help the robot. And helping here really means like taking it and just navigating it, pushing it a little bit, a meter away from its kind of tricky situation. Well, that's good. It can carry on this task, but if it goes back there, it may end up in the same situation again. And that's why you can use, again, some machine learning, and we're using here something that's called so-called Gaussian processes, which is a way of imitation learning. So if we ever encounter a situation again that we've seen before, we're really trying to almost replay what the humans have done. Right? If they found a way out of our tricky situation, why not use that information and to basically do the same again? And this was kind of typical situations, very narrow passages where the robot just wasn't comfortable going through because it was so narrow, and its sensors were not quite sure where it exactly was. And whenever we had these sort of situations, we could use that to push the robot along to overcome that. Now, that's a good way, again, to people accept to some extent robots' failures, but they will not accept the thing asking again and again. And we had got a lot of evidence and a lot of anecdotal feedback from people in that care home where they said, "Oh, it's stuck there again. It's stuck there again." And that was basically what motivated this work. And now it actually will not fail in the same places again. It has a massive positive impact on how much people trust these robots to do their jobs properly. Now, I've also said it's not only about not doing the same thing again, it's also about avoiding like the really stupid things where things fail. And I mentioned software engineering before. And that's a kind of really typical problem that we see in particular at a university. Right? We've got a young team of developers. Some are doing their PhD, some are doing their master thesis, and they contribute to this complex system of a robot here with a small piece of their own work, of their own research. And then they're more interested in getting their thesis, right? Or just kind of getting the next scientific paper out. And they are not necessarily well-trained software developers. Right? They are good researchers, but not necessarily good software developers. So it becomes a challenge to actually build a system that is stable and that is reliable. And if it is not reliable and things are not properly tested, then fatal things can happen. So that's why also we've done some research that is related to the area of software engineering, where we done complete automated systems testing. So what you do there is you take these challenges, that you don't have well-trained developers and so on, and you kind of constrain them a little bit into this overall software development life cycle. And some of you who've basically studied at university, you will all be familiar with software development lifecycle, is that you specify, you develop, you evaluate, and the results of that evaluation go back into your next development cycle and how you improve the system. So that's something that we need to do all the time. It's part of our daily life in computer science. Robots are quite tricky, though, to embed into this because they're actual physical entities, and you cannot really test them. It's just not feasible with so many developments happening in parallel to always test everything in real world so easily. And so there's a sort of standard software development model. We use GitHub a lot, which is a kind of source code repository, and has a lot of features, so-called pull requests. That is basically somebody proposing to change the system in a certain way to improve it. But we must make sure before we accept that into our main code that actually this will not have stupid side effects on the overall system, and that it will actually still ensure that the robot does what it's supposed to do. And that is all about test-based development. So we have certain test cases. So that means we, for instance, here's a very simple test case around our navigation system. So whenever we change something on the robot's code base, we must make sure it can still navigate from A to B reliably. It can also do like more complicated things. If there's an obstacle in the way, go around it. It doesn't crash into it. And in that context, we have developed a lot of simulation environments, or sometimes even you could say that they're somewhat digital twins of the real world. So they are it's a replication of the actual physical world in simulation, and then all embedded into the software development lifecycle, that whenever somebody proposes a change to the overall system, it automatically fires up a simulation environment on one of our servers, and that then automatically tests if actually the robot can still do these defined tasks. Now, you can't test all the adaptation that you have got out in the wild there, but you can ensure that at least you've got a solid software base here. And that's been now been used by most of our developers. That's the kind of principle here that we have whenever somebody wants to change a system. It runs through some of these automated so-called unit tests, or sometimes even actual full system and integration tests. And it gives you the result of this sort of testing directly in your software management framework, as you see here. So a green tick in here means, yes, these tests have all passed. It may be now safe to include this new feature that one of our students, one of our researchers, one of the PhD students has implemented and put it onto the live system that we run, that we deploy into different scenarios. So that's something that we've done, and we've built quite a huge software repository around this principle now, that a lot of people also outside of Lincoln use to actually have the robots navigate and run around in many, many different places. So these robots are running at Honda Research, for instance, where they're running in sort of warehouses and so on and so on. And talking about these sort of different applications, I'm going to just give you a glimpse of some others. So this was a little bit of an in-depth analysis of this system that we had in this care home. As I said before, so now we've kind of spread out into many, many different domains. But they all share the same sort of ideas, right? We want competent robots that are reliable and that they can adapt over time on the jobs. And one of the biggest area that we're doing in Lincoln in this context is in agriculture. So I'm going to quickly look into some of these aspects of what we call human-centered robotics in agriculture. This is work we do very closely with a company called Saga Robotics. So they built this Thorvald robot that you see here on the screen. And we've got a number of different projects, many of them funded through Innovate UK. So this is directly working with industry partners to actually advance autonomy of robots in different applications. And we've got a number of them in agriculture. And while, the overall vision of you can automate a lot of different aspects in agriculture, and there's a really strong drive for that. I mean, there's at the moment a big challenge for a lot of people in agriculture because we're losing some of the workforce. It's not the most appealing job to do. Brexit has to be mentioned in that context, proposing really big challenges on the agricultural sector. And they really are craving for increased automated solutions for harvesting, for crop care, and so on. One system that we have looked at here is using these robots for logistics tasks, for having them actually roaming around a farm and help supporting human pickers, not replacing them, but actually making them more productive. Because at the moment, they spend up to 20% of the time carrying crates around. So they pick fruits, and here's a strawberry farm where we've done this. This is actually part of the Rice Home campus of the university where we try these things out. And here the idea is just simple. Well, let's let these human pickers do what they are really good at. So very good and very fast at picking these things. And let's take this mundane task of carrying things around of them. Let's relieve them of this. And the simple way you could think of it is that you have an interface which allows you to summon a robot to you. Now, you are picking, and you've got a full crate, and once you have this full crate, you want to get a robot to you to take it off you. It's almost like shouting somebody, "Oh, can you help me? Take it away." In that sense, very simple, right? So we have quite reliable, over the years, built navigation systems that allow these robots to go around very reliably on their own, a little bit like autonomous cars, if you want, using also very similar sensors as autonomous cars do, but in these sort of challenging agricultural environments. But this question is then, how do we interact with these people? There's two different interfaces that we've actually originally developed here. One is a web app where you can just say, "Oh, give me a robot on my phone," and the other one is a more affordable, directly like weather-proofed system, what we call smart trolleys, that people, when they are picking, they have this little trolley. It's mounted on this trolley, and then whenever they need a robot, they just click the green button, and it will come. And if they have put everything on, they just send it away by clicking another button. Interesting and important for us, obviously, is to know where should the robot actually go if somebody summons it, and which route should it take along a farm to do that. So again, there could be a lot of learning. I'm not going to go into these sort of details here. What we're learning in this setup is when will people likely actually need a robot, so we can anticipate that and have a robot lingering nearby. Also, what we can learn is which routes are blocked, which routes can I take, and that may be something that you really only learn on the job. So you may have gone somewhere, hit a dead end, have to go all the way around again, and that's what you want to avoid, right? So there's an opportunity to learn and get better on the job here. Very quickly, I'm going to go through how we solve the problem of where should the robot go. If you have a phone, you will be quite impressed often with the accuracy of your localization. When you use something like Google Maps or Apple Maps, you see it shows you your position. It only shows that position up to, if you've got a very good phone and you're in ideal conditions, maybe around 3 meters accurate. Now, 3 meters accurate is great if you want to actually navigate a city. If you want to navigate between these rows of strawberries that we've got here, which are about 1 meter apart, that could be very bad. That could be very wrong where you are, right? So if you are standing here like this poor guy, and the robot would have gone just 2 rows down from where you are, it's useless, right? You could duck under these tables if you wanted, but that is basically immediately destroying any trust into this robot that it actually can do its job. So first thing, we need to be able to really localize people correctly. Now, there are very expensive solutions to do something like differential GPS. We don't want those, right? So these are really tricky because they are so expensive, and you want to have hundreds of these devices, and you can't afford paying £2,000 for each one of them. But luckily, we can use computer science, we can use machine learning, we can use what we call probabilistic robotics. And from this, we integrate different readings to actually come up with where they are likely going to be. And we're using something that we call topology. It's the kind of layout of the farm. And we know that people will normally just travel along a row and not jump between them. And we can use that knowledge, that's about the environment here, to constrain how these are moving. And then there comes a lot of kind of big words in here. Particle filter is a way of achieving these sort of things. We can model and we can learn how long people usually take when they move along and are picking, so we can anticipate how fast they will move. And everything that kind of violates these assumptions is very unlikely. And just by putting these assumptions in, we can go from very noisy readings, as we see here, where this is often in the wrong rows. The green one would be the correct one, and the red ones is when the system thinks they are here and this is actually incorrect. But we can correct that to only get the correct readings by integrating them over time and putting these constraints in place. Shows again, if you learn on the job how fast people move, etc., that's how the system gets better. This is the information that we need to actually learn and to localize these people correctly. So if you have that, then it becomes a question of which robot should go where and how do we avoid them coming conflicting with one another. It can get quite busy. We don't want a traffic jam of robots on these farms, especially these rows are very narrow. So that's where so-called fleet coordination comes into the play. We will have more than one robots. We're talking about 50 people and maybe 10 robots serving those doing this transportation. And then you can do sort of planning in this so-called topology, ensuring that, yes, you know where the robots are. We know also where these pickers are, and we can route them through this maze, if you want, so that they don't conflict with one another. And there's a lot of kind of typical planning that you will also learn at the university when you do modules in AI. The actual underpinning path planning here is an A-star path planner along these sort of graphs. And then you can find a good trade-off of how many robots you need and to serve but many pickers, and you can do a lot of simulations to also find the right trade-off. Not going to talk much about this now. And here's a kind of simple system where you click a robot. We've got 2 here in this system. Somebody clicked it to come here. If one robot is assigned the task, it will set off to do this. Somebody else standing here will eventually click that button and wants to get another robot there. I'm going to just fast forward this a bit so that we see both of them moving. Right, and so we see that they can then go along. Now this place is free, so this robot can also go in parallel, and they just ensure that they are not conflicting with one another. Excellent. So we can also then, of course, this is still human pickers. We're also doing a lot of work in automated picking. So here's some initial prototype that we're working on with this company, Saga Robotics, where you have to solve a lot of the challenges, be it vision challenges, so that these robots can actually detect these fruits, can assess whether they're ripe or not ripe yet, and then the actual robot arm control to reach for those different fruits and snip them off and put them in a punnet is something we're working on. So there's a much more advanced prototype than this early one at the moment in development. And if you ever happen to be at our Riceham campus, just north of the city, that's a lot of very exciting development happening there. And once we get the new fruits into the next season up there, we will have hopefully got them all harvested by robots. While at the moment, they're still being harvested by humans there. Oh, well, not at the moment. In this last season, we haven't got any strawberries at the moment, I'm afraid. So, and there's a lot of, again, machine learning, deep learning, often called here, to actually understand what these strawberries look like, to discriminate between the right ones, assess their size, estimate their size, and then be able to only pick the right ones. And the good thing is with these robots, when they go through that, it's not very expensive anymore once you've got them, right? So you don't have to pay wages to people that do the picking anymore. You can just afford to only do very selective harvesting. So you send this robot through every day rather than just once or twice a week, as we do with humans at the moment, and you get the fruits at the real prime point of their ripeness. Overall, having strawberries in your supermarkets that hopefully last longer and are nicer. I'm going to quickly move on. We're going to quickly come back to also these sort of safety aspects. Now we've got these robots out in the field. They're relatively big. And I like this video. This is a late night session that I had with a company in Vienna who developed these so-called air skins. And we need to move forward to actually make these robots safe. We have at the moment, they are working there. They're doing some of their jobs. But the moment they come close to humans, we have a challenge here that we must guarantee that they're not going to cause harm. So a lot of the work coming before already about how we can ensure that our systems are reliable and are not falling down the stairs. The same also applies, of course, if you have these robots going out in the field, relatively strong motors, and we need to make sure that they are not causing harm. So this is just one concept for a robotic arm that I was brave enough to go into the workspace of such a robot. And you see this one is just also an engineering challenge to stop the powers to the motors here, or to kind of stop them moving the moment they make contact with anything. And we've done a lot of work also in the context here to perceive humans reliably and then implement safety features on these robots. So there's a whole kind of project around these sort of safety aspects that we're having with the Lloyd's Registry Fund, that actually foundation that looks very much into these sort of aspects of how we can ensure autonomous robots in the field and get certification for them without having cages around them. Quickly on continuing this journey, so we also have robots that are, again, heavy, possibly carrying heavy loads, that are in logistics. You may know these sort of logistics applications from Amazon, Kiva robots, and there you again have this full separation. You've got the humans operating on one side, and then you've got all these robots roaming around in a warehouse on the other side, not to actually share any space between them. Now, that's all nice and very efficient if you can afford to build a fully roboticized warehouse to start with. It's not really good if you are a smaller company that wants to introduce automated logistics, and because then you can't build this completely new warehouse, and you just need to integrate some robots that can live in the environment that is already there, where you may have some people roaming about and where you will have some autonomous vehicles also roaming about, and they kind of need to share the space. So similar challenges, and you see this is also a logistics operation here, and we've done a lot of work here in this context of human-aware navigation. Again, this sort of fleet coordination, so which robot goes where so that they don't block each other. A lot of perception challenges, again, do we see this person? What are they doing? Are they seeing us? And so it comes back to actually integrating this perception of humans into the navigation routines of these systems. And here's a short video of these sort of autonomous forklift trucks that we're running in the National Center for Food Manufacturing, which is also part of the University of Lincoln. It's down in Holbeach, where we've deployed this as a test installation, where these robots are roaming about autonomously in human shared environments and ensuring still that they are safe to operate. Talking about other robots going into the wild, just my last one that I'm going to briefly talk about. Very excited about this particular project. It's with the Collection Museum in Lincoln. And we had this robot deployed there since 2018. And currently, of course, due to COVID, it's on hold and it's not operational. It's waiting eagerly to come back, because this is again the idea to learn on the job. Similar robot as you've seen in the care home. And it gives tours to visitors. So you can go there, not at the moment, but the moment it's fully open again, and be guided around the collection on different themed tours. And again, we want to get better on the job here, right? Well, we've started off with handcrafted tours that the educators of the museum developed. The idea is to actually evolve those tours and learn what people liked, what people didn't like. Did they want more information? Did they want less information? Is this a particular artifact that they enjoy? Is this one that they don't enjoy? And it's a similar thing of actually using learning routines, machine learning, to adapt on this job. And we can use, again, in machine learning sense, the feedback from people. Did they carry on with that tour? Did they want more information? Did they abandon the tour? Did they just walk away because they were completely bored? And then we can do something that is called reinforcement learning, where we basically take this feedback, where we know that people are engaged or not engaged, to change the behavior, to decide for the robot autonomously on its own, oh, should I give some more information to these people? I can even estimate how old they may be, what gender they are, what sort of group size there is. I may have a different behavior for kids than I may have for adults. And this sort of information that you can gather right there on the fly is fed back into this system to actually see these tours that the robot offers to actually improve over time. So that's an ongoing project, as I said, currently paused. Very excited once we're allowed back in, and then you can follow Lindsay Robot around in the Collection Museum at Lincoln. So I hope I gave you a little bit of an overview of the different projects we're doing with robotics all around this theme of adaptation and kind of increasing the capacity of the robot on the jobs. I did this all because, indeed, humans are the robot's worst enemies, if you want. And I give you a few of these kind of more or less entertaining examples as my last round here. This on the left-hand side here is actually showing a woman that has been captured on our camera. She's still having the finger up here because she just pressed the emergency stop button. People like messing around with robots. If they are out there, they will try things out. This emergency button that was implemented here, it had to be implemented because, you know, it was part of the actual agreement with the care home that they can push an emergency stop button and it won't do anything. It won't move. It won't get in their ways. And twice a day, that was our main job, to as remotely administrate the system. It was very reliable. Twice a day, we had to assess a situation where people pushed the emergency stop button. And the same happens in the museum. It's kids hitting the emergency stop button because it's a bright red button that needs to be bright and red. But people don't really think about the consequences. They're, you know, playing around and enjoying these sort of seeing what happens. And here's another example of seeing what happens. This is only, we haven't got the live video. This is the actual data from the robot, and you see these lines moving here. What happened here, this robot was standing in front of the chapel entrance. This is the chapel entrance in this care home. And just by talking to people later on, we wondered what was happening. This indicates that the robot got lost, right? It's, if these lines don't line up with the actual walls on a map, it means the localization of the robot is incorrect. We wondered why it wasn't moving. So why all of a sudden did the robot why was the robot mislocalized? Because it stopped, it alarmed us, it sent us an alert saying, oh yes, I'm lost here. And what happened was that the priest was annoyed that this robot was stood in front of it, and he forcefully just pushed it out of the way. So people don't, you know, you wouldn't do that with a human. So we need these sort of ways of interacting with people and actually, you know, react to their responses to those guys. In this case, what we actually allowed was a push feature. So the robot would notice when it was pushing and would basically disengage its brakes and would be, you know, would be happy to be pushed around and say like, all right, okay, I move away now. So these are things that come from iterative design when you actually put these robots out in the wild and you learn these sort of lessons. The last one is not a video of ours. This is from a study they've done in Japan. This is again a robot out in the wild of a shopping mall and doing similar things. Information terminal, you know, it it tries to ask people to kind of follow, direct them around, etc. Here are some kids. Right, these are some kids playing with this robot, and they are really trying to, well, bully it. Right? In that sense, this robot just wants to get on with its job, and here we see they're having a lot of fun. And indeed, they don't treat it with the greatest of respect, I would say. Forcefully moving its head, kicking, pushing, all sorts of things happening. So very interesting from this, and this is very similar to the situations we observe in the care home. Not in the care home, in the collection museum. The worst I've seen where the robot basically notified us that it wasn't working properly. The reason for that was that somebody had wedged a half-eaten sandwich into its slot where its sensor sits, and so it couldn't actually see properly anymore. Again, so we see that, you know, we always talk about, well, should we give robots some citizenship? Should we treat them like humans? I think we're far away from that. People do not treat robots as humans. You've got all these kind of practical problems. So this is an example here where the robot couldn't charge anymore, and we wondered what was broken. What actually was broken, it had mopped up a chewing gum that was on the floor and was stuck to its charging contacts here. So that is kind of where I want to come to an end, and just going to give you a few more fun examples here of things that can go really horribly wrong. So trust needs to be mutual. I think this is the thing. So we also need to be able, robots need to be able to trust humans. If humans abuse robots, if they bully them, if they give them wrong examples to learn from, their behavior, if they adapt, will also deteriorate and probably not be trustworthy. So it's about kind of what they learn and what they adapt to. And machines are not treated as social equals. So I would even say they shouldn't be considered as social equals. We've got particular challenges with robots. And that's a very, very interesting ongoing debate. Here's another example of again of how often things fail in our care home. And quite often they are associated with events that are out of the ordinary. So here was one where they had a Christmas market and they had stalls put up in the environment, and all of a sudden the robot couldn't navigate properly anymore. Another one was again, robot calling us saying, oh, I can't operate. What was the reason? Well, somebody had put a chair right on top of its charging station. So the poor robot just couldn't get any energy anymore and was running out of power and really couldn't go back to its charging point because people had messed in an environment. And again, it can't really move chairs. They like to also put stuff around in other places. So this was a place where the robot should go for its infoterminal services, a sofa put there, and the robot just miserably failing with these sort of things. Or sometimes they put plants around right on the kind of pathways, and they change the overall layout of these environments. So these are kind of typical challenges that we have these days. And I said, well, we may have motor failures or even really bad things. So, very similar to the Daleks, our robots can easily be stopped from taking over the world here. These stairs are a robot's worst enemy, at least as we offer this, as it seems. But there's a lot of importance that we can see from just actually being able to adapt on the job, getting better. And that's the kind of key message. While the robots may come with some innate behaviors that we can code, and we must make sure we actually implement those very reliable, they still need to be able to learn and adapt to the specific scenarios. And they mustn't do the same mistake all over again. Right. So just some questions putting out there that I think are somewhat interesting that you may also kind of explore yourself a bit further. To what extent can we say that robots are social equals? This sort of continuous learning, is that actually a core for trustworthy robots? And I believe it is, because we really don't want to see robots doing the same stupid mistake again and again. Because so far our evidence is that this is going to really deteriorate any of these trusts. We need to have these robots going out into the wilderness, right? They need to be deployed, as we call it, and they need to be able to learn on that sort of job. So they need to exploit these experiences. And as we see them moving forward, going into more and more of the different domains, application domains, scenarios, be it care, be it agriculture, be it logistics, we will see that they will actually more and more work with people. We are on a journey in automation. Right? We are not directly say, this is the moment where robots will take over. It's an evolution, and I would say there is no robotics revolution. Robots have been around with us for a long, long period of time already, and we've been using them. We only see now that we're working closer with them. They were more separated before, and now we see them actually sharing more of the space with us. And so we will get used to that. We will adapt as humans, but at the same time, we need these robots to adapt to us. And that's where I will end my little presentation. And I don't know if you had any comments. If you have anything to say, put it in the chat here. And I'm sure my host, Paul, will come back in and say if there's anything there. Or Paul, if you've got any questions, fire away. I'm going to have a look if I find some of these questions.
We just have the one, Mark.
Yeah.
One question for you.
How long does it take?
Yes.
How long does it take to test from development to live deployment of new function typically? Yes, Chris. So it's an iterative process, and that's all I want to kind of really say. You want to start off with something that is a basic functionality, and then you want to evolve that as you go further. So we see normally we start off with what we often call a baseline system, that does the job well, just about. And then you want to integrate into that and improve it. So really, robotics is absolutely the kind of key example of iterative software development, especially when we come to these sort of systems. So that's also, on the one hand, the development is iterative, but also then these sort of adaptation as they go along is very iterative. So it's difficult to say how long does it take to test. The sort of process when somebody implements something to actually run this through the simulation and to kind of our code review process, that's usually quite quick. Normally features are going into the beta stream, if you want, or the alpha kind of release stream very, very quickly. But then to actually go out and say, well, we're going to deploy this for a larger study, that then usually means a lot of on-site testing, and that could easily be like 1 to 2 months for these sort of systems that we're talking about, where we have actual people to deploy it on site and run it there. And that's the kind of typical thing. And then you must adhere to the typical software development principles of having a stable release. And of course, if we work with other industries and so on, we only ever release from this sort of stable channel. That's the sort of deployments, and then run for long periods of time. So in this case, for instance, that was there for a year in total. And obviously that was clear structures of feature freeze, just bug fixing for a month, actually continuous testing on that side, and then letting it roam freely. If that's all the questions, I think we've just hit the hour here. Thank you for your attention. It was lovely, and I hope you had a bit of an overview of what sort of robotics we're doing at the University of Lincoln. And this links in with a lot of the actual teaching side as well. So we've got modules specifically on autonomous mobile robots, where we see how these robots move. We've got a lot of the work in AI and machine learning. The basics are also taught in these modules. And then we've got a dedicated master in robotics and autonomous systems that really is about developing on basis of these sort of systems further. So at the moment, I'm quite excited to see the work by our students that are doing robot programming, where they have to take one of these Thorvald robots currently in simulation and actually have to develop a system that can weed fields autonomously by actually doing selective spraying. So it's a really fully autonomous robotic system that goes out onto the field, identifies where there's crops and where there's weeds, and then selectively tries to eradicate the weeds that are out there in the field. So you can see that this sort of it's addressed in many, many different areas. And here again, different aspects of machine learning of how you can actually discriminate weeds from crops come into the play, as well as navigation challenges, because you may have quite a number of obstacles and challenges when you go out into these farm environments. Good. Thank you very much. And if there are further comments on the video later on, you may also get in touch with me. You will find my email address on the university's website. Thank you.